In this video, we'll cover mass defect and binding energy. In this image, you will see protons and neutrons. Protons are the blue ones and the neutrons are the red spherical. They're coming together to form this fluorine isotope, fluorine 19 in particular. Why? Well, if you count the number of protons, 1, 2, 3, 4, 5, 6, 7, 8, 9. So fluorine has an atomic number of 9, hence you see 9. That means the neutron probably there's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 neutrons, so fluorine 19. Well, each of these protons and each of these neutrons, they weigh something. So they have this predicted mass in which if we were to combine all of them together, they'll carry certain weight. In order to calculate the predicted mass, we'll need to utilize some values, and I have those values on the right here. Each proton mass is 1.00728 AMU. One neutron is 1.00866 AMU. AMU is a unit of atomic mass unit. Just like kilograms, pounds, grams, they have their own units for mass, and so does this one. So AMU, atomic mass unit, is the unit for this particular subject. So let's go ahead and calculate and see what the predicted mass might be for if I were to combine all of these together. Since there are 9 protons, so here protons, 9 of them, and each other proton is 1.00728. And the neutron, there's 10 of them. We can multiply that by 1.00866 AMU. So these are all in AMU. And I can take these multiplication and add them up and sum them up. Where am I getting these two values? I'm getting it from how much each proton weighs and how much each neutron weighs. So let's go ahead and calculate this out. So we have our 9 times the atomic mass unit for the proton, 728, enter, and then we're going to add that to the neutron, multiply by 1.00866, enter, and I get 19.15212. Okay, so this is altogether 19.15212 AMU. Right. So that's their predicted mass. However, the actual mass when they come together to form a fluorine is actually a little less, 18.9984. And this is where the concept of the mass defect comes in. Oh, I apologize. It's covered and it's just a mass defect. Mass defect is equal to the predicted mass minus the actual mass. So my predicted mass was 19.15212. The actual is 18.9984, meaning that there was a little less mass consumed, or I should say little less mass as this was forming. So what's the rest of the mass? Where did it go? Well, that mass defect is what we're calculating. And so let's go ahead and subtract these two values. And if you subtract these two values, you should get 0.1537 AMU. And the reason why I put it in only in this place, in the fourth of the right of the decimal, is because this ends in the fourth, and by sig figs, you have to go with the one that has the more of the higher decimal point. So this one has more of a higher decimal point than these guys. This one goes all the way to the 5th decimal point. So that's your mass defect over here. Well, the mass defect was converted into energy when the nucleus was formed. Then how much energy? Meaning that this mass defect, this mass was actually had the ability to convert into energy as this nucleus was formed. And to calculate that energy, we use this famous Einstein equation, E equals mc squared. The mass that we just saw for the mass defect goes into this m. Then the c is the speed of light. But the m right here does not represent the AMU. So energy, if I were to put what all of these mean, energy represents joules. M represents that mass, the mass defect we just calculated, but it has to be in kilograms, not AMU. And the C represents the speed of light, so it's 3.00 times 10 to the 8th meters per second. So we'll have to get that mass figured out a little bit and to calculate the energy. In fact, I have all of these 3 energy points that I would like to kind of talk to you about and to calculate together. We want the energy per nuclei, so every one nucleus that you make. Energy per moles, so every moles that we make, how much energy is being released. And the energy in electron volts, this is more for physicists, per nuclei. So let's target energy per nuclei. So first we need to convert that mass into AMU. So let's go ahead and do that. So I'm going to do that right on top right here. So our mass from previous slide was 0.1537 AMU. Utilizing on the right-hand side the unit conversion, every 1 AMU, so I'm going to put that below, 1 AMU, so that the units could cancel out, and 1.66054 times 10 to the negative 7 kilojoules. So let's calculate that out. 0.1537 times 1.66054 times 10 to the negative 27. So quite big, small number. And I would get 2.552 times 10 to the 24th. So I'm going to go up to 4 sig figs. So that would give me 2.55, and then rounding up 3 times 10 to the negative 28 kilojoules. Okay, so now that we have that, we can plug this into E equals mc squared. So E is equal to mass, which is 2.553 times 10 to the negative 28 kilograms. And then multiply that by the speed of light, but not just the speed of light, but to square that speed of light. Okay, so let's go calculate that. So already I have my mass over there. So I'm going to put multiply by the speed of light. I'm going to put it in parentheses. So that I can square just that portion. And I would get 2.297 times 10 to the negative 11. Okay, and since the speed of light is in 3 sig figs here, let's go ahead and put it in 3 sig figs, 2.30. Negative 11, oh, by the way, this is meters second, and it'll be kilograms meter squared second square. Kilogram meter squared second squared is also known as joules. So this whole thing is actually joules. So we can erase that out and put joules. And this is for every nuclei. So I'm just calculating based on every one nucleus that we have been forming. So nuclei. Okay, so here is my key for this particular energy joules per nuclei. What about energy or joules per moles? Well, we're going to take that 2.30 times 10 to the negative 11 joules per nuclei. And if you recall from many months ago, maybe a year ago, there is an Avogadro's number that's 6.022 times 10 to the 23 of anything, and this one happens to be nuclei, is equal to 1 mole of it. So this is your typical Avogadro's number. So if you were to calculate this out, so I already have my joules per nuclei there, so I'm going to go ahead and multiply by the Avogadro's number, 10 to the 23rd. And I would get 1.38. 1.38 times 10 to the 13, I believe. 13 joules per mole, okay, since nuclei cancel out. Great, so that's a significant amount of joules, okay, significant amount of energy that was released as it's going through this formation from an individual proton and neutron coming together to form a fluorine molecule. What about in electron volts? Remember that electron volt is another way of showing energy, and 1 electron volt, as shown on the very right, 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. So it's looking for in per nuclei, not per mole. So I'm going to utilize this one on top to you do the unit conversion. So 2.30 times 10 to the negative 11 joules per nuclei. And then I have the joules on the bottom and 1 electron volt on top, so we can cancel out the joules on both sides. So I'll go ahead and cancel this out and cancel that out. So I have electron volt over nuclei, and I'm going to calculate this. I'm going to have to go back and just kind of type in everything. 2.30 times 10 to the negative 11, parenthesize. And then I'm going to divide that by that 1.602 times 10 to the negative 19. Okay, hit enter. So we get 1.44, and if you count the decimal through, 1.44 times 10 to the 8th. Okay, so I have that already written on the side as I'm looking to the right. That will be 1.44 times 10 to the 8th electron volts over nuclei. Okay, so we calculated all the joules energy, okay, based on the mass defect. So we took that mass defect and converted it into energy. So essentially, I can rewrite this in or illustrate this concept. So here's my protons and neutrons. There's 9 protons and 9 neutrons, and it's forming into an atom like this, into a nucleus. And then as it's doing that, some mass has been lost, and that mass was converted into energy. So I could say plus E because it's been released. But we can think of it in another way as well. We can say that, well, we have this we have this proton here, and we can go it in the other direction. So I'm going to draw the arrow going in this direction now. If I were to go in this direction and they got all dispersed, well, we need to require that some energy in order to disperse that apart. Well, that energy is the same value as here. And in fact, that energy is called the binding energy. It's the energy required to break the nucleus apart. So a lot of the textbook will say this, but it also goes in the other route in that it's the energy that is released when the nucleus is formed together by all the individual proton and the nucleus. And the value is exactly the same, the mass defect. So let's do a learning check based on helium. What is the mass defect of the nuclear binding energy for helium that has an actual mass of 4.0026 AMU? You're going to calculate the binding energy per nucleus, joules per moles of nuclei, and electron volts per nucleus. So you're going to try this and come back and check. You go by step by figuring out the predicted mass, then the mass defect, and the mass defect all the way up to the joules, utilizing E equals mc squared. So try it and come back and check the key. Here is the key. So I wanted just to show you where all the answers are, just in case you're scrambling for the answer. This is mass defect over here. Okay. And then we have joules per nuclei here. And joules per mole here. And then electron volts per nucleus, or nuclei, I should say. And I think I forgot to write per nuclei.